Hello everyone, a very good evening to all. Once again, I welcome you all for this webinar session on the course Atomic and Molecular Physics, which is being flowed this January 2025 session by NPTEL with the course code NOC25PH04. Myself, Vivekananda Naik, I am a PMRFTA of this course. I am a PhD research scholar in the Department of Energy Science and Engineering Plasma Physics Laboratory at IIT Delhi. So today we'll be discussing a few problems that will be based on the week 12, that is the last week lecture of the atomic and molecular physics course. Now talking about the course content of the week 12, the week this week's lecture was mainly about Raman spectra and some elementary idea about electron spin resonance spectroscopy and nuclear magnetic resonance spectroscopy are also briefly discussed. So we will be solving a few problems that will be based on this following concept. But before that, let's get a brief idea about the Raman spectra. Now, so Raman spectra. So what is Raman spectra? When a monochromatic light is incident on an organic liquid, then the light is scattered in all directions, and it has found that the scattered light contains a number of components, and the scatter light was different as that of the incident light. So if the frequency of the scatter light is exactly equal to that of the incident excited light, then that is called as relay scattering or relay line. And if the frequency of scattering line is scattered line is not equal to the uh, incident or exciting line, then that is called as Raman lines, that is known as Raman spectra, and this effect is called as Raman effect. So, in case of Raman spectra, if you see the spectra, so suppose this is the frequency axis. So now in the frequency axis, so there will be a central line which is equal to that of the incident line or exciting line, and this line is called as relay line. Relay line, and there are other two lines that are not equal to the incident line. These are called as Stokes and anti-Stokes line. So this is, so on the left hand side with a difference of delta mu, this is called as Stokes line, and the another component that is also have the same spacing as that of the Stokes line is called as anti-Stokes line. Anti-Stokes line. So if the frequency of the incident light is mu, suppose the incident light has the frequency mu, then suppose the scattered light has the frequency, suppose the scattered light has the frequency mu prime, then the value of mu prime, what will be the value of mu prime? Then mu prime will be mu minus delta mu. So there are three cases. Case 1, if delta nu equals to 0, then nu prime equals to nu, and this is called as relay line. And case 2, if delta nu is greater than 0, then nu prime is less than nu, that is called as Stokes line. Case 3, if delta nu is less than 0, then nu prime is greater than nu, that is called as anti-Stokes line. So these are the three components of Raman spectra. Now there are different types of Raman spectra. One is called as Raman vibrational spectra, another is called as Raman rotational spectra. So in case of Raman vibrational spectra, if you talk about Raman vibrational spectra, Raman vibrational spectra. Then, so if the molecule is considered to be behaving as a simple harmonic oscillator, then this and then its energy is given by V is equals to V plus half H C omega E, where omega is the vibrational constant. Now the transition occurs. Suppose the transition occurs from nu to nu prime, then H nu will be E V prime minus E V. So nu bar will be E V prime minus E V divided by HC. So Azil, I will request you to mute yourself. So this will come out to be V prime plus half omega E minus V plus half omega E. So it will come out to be V prime minus V into omega E. So this wave number will be delta V omega E, and the selection rule for Raman pure vibrational spectra is selection rule is delta V is equals to plus minus 1. That implies the wave number change will be plus minus omega E. So this is the Raman vibration spectra. Now if we discuss Raman rotational spectra, let me add another slide. So if we discuss about Raman rotational spectra, Raman rotational spectra. So we know the energy of a rigid rotator is given as Ej is equals to J into J plus 1 BHC. So however, for Raman spectra, the selection rule is Raman spectra. The selection rule is delta J equals to plus minus 2. So the transition occurs from J to J prime. So J prime will be J plus 2, or it will be J minus 2. So corresponding to, suppose the transition occurs from J to J prime, then in that case what will be the change in wave number? So it will be Ej prime minus Ej by Hc, which is J prime into J prime plus 1 minus J into J plus 1 into B, where we know B is the rotational constant, and the expression for B we have also discussed a few problems that are based on the concept of how to calculate the, for example, if you know the rotational shift, then how to calculate the moment of inertia. All these type of problems we have already discussed. Now suppose the transition occurs from J to J plus 2. Suppose transition occurs from J to J plus 2, then what will be the wave number? It will be J plus 2 into J plus 3 minus J into J plus 1 into B. So if you uh, multiply it, it will be J square plus 5J plus 6 minus J square minus J into B. So it will be 4J plus 6 into B, or if you take 4 common, 4B, it will be J plus 3 by 2. So this is, so so This is for anti-Stokes line. Anti-Stokes line. Then if the transition occurs from J to J minus 2, so in that case it will be J minus 2 into J minus 1 minus J into J plus 1 into B. So it will be minus 4J plus 2 if you multiply it into B. So it will be mu prime, it will be minus 4B J minus half J minus half. So this is the expression for code number shift in Stokes line. So these are the concepts. So you should remember that the selection rule, it is delta J is equal to plus minus 2 for Raman spectra. However, for rotational spectra it is plus minus 1. So that is the main difference between Raman spectra, Raman rotational spectra and rotational normal rotational spectra. So these are a few things that we discussed about Raman spectra. Also there are some to study the effect of Raman spectra there are different theories. One is classical theory of Raman spectra, another is quantum mechanical treatment. So all these things that has been covered in the week's lecture. So let's start solving a few problems that are based on these concepts of week in the lectures of week 12. So question number one says match the column X with column Y, where in column X it is written I is electronic energy level, 2I is vibrational energy level, 3I is rotational energy level, and column Y it says A is infrared spectra, B is far infrared and microwave spectra, and C is UV spectra and visible spectra. And these are the options: option A, B, C, and D. So we have to match the column X with column Y. So where you can see in column X there are energy levels of a molecule. It is electronic energy level, vibrational energy level, and rotational energy level. And in column Y there are different region of electromagnetic spectrum. So basically we need to match the transition corresponding to which transition, or the transition that occurs between which type of level, then that corresponds to which section or which portion of the electromagnetic spectra. So this will be the thing that we need to do in this particular problem. So I'll give you a few minutes to think about this question and find the correct answer. What will be the matching of column X and column Y, and then we will discuss. So if you remember the discussions we had um, before a few weeks, so if you talk about the energy levels, then first there are, suppose there are three levels. These A, B, C are called as electronic levels. So these are electronic level, and then corresponding to each electronic energy level there are vibration energy levels. So there are vibration energy levels V1, V0, V1, V2, like this, and corresponding to each vibrational level there are a number of rotational levels. So these are rotational levels and these are vibrational levels. So now if we talk about the energies of electronic spectra, so we know the energy, if you talk about the energy for electronic spectra, for electronic spectra, the order of energy is 10 electron volt, and for vibrational spectra, the order of energy is 0.1 electron volt. For rotational spectra, the order of energy is 10 to the power 3 minus 3 electron volt. So we know the for electronic spectra, it lies in the region of UV to visible regions. As you can see, this is the region UV to visible region. So UV to visible region, and in case of vibration spectra, it is the order of energy is less than that of electronic spectra. So as you can see, this is the increasing wavelength axis. So wavelength increases along this and frequency increases along this. So since the energy is the order of energy is smaller as that of the electron spectra, so it will lie behind. So this is the infrared spectrum, which lies after the visible and ultraviolet and visible spectrum. So vibrational spectra corresponds to infrared region. Infrared region. And if you talk about rotational spectra, the order of energy is even lesser, that is 10 to the minus 3 electron volt, and the rotational spectra lies in the region of far infrared and microwave um, part of the whole electromagnetic spectrum. So this rotational spectra, that is related to the rotational energy levels, that corresponds to far infrared and microwave spectra. Far infrared and microwave spectra. So as you can see, so it is so this direction is decreasing energy, decreasing energy. So as we go from X-ray to UV to visible, then infrared, then microwave, so the energy decreases. So the correct option will be, so electronic spectra, electronic energy level will be UV and visible, then vibration energy level will be infrared spectra, rotational energy level will be far infrared and microwave spectra. So what will be the correct option? So the correct option will be I is C, 2I is A, and 3I is B. So the correct option is option A. I hope this is clear to everyone. So the electronic energy level, it has energy of the order of 10 electron volts that lie in UV and visible region, because they are of higher energies, and for UV region the frequency is higher, so the energy is higher. And in case of vibration spectra, the energy level, the order of energy is 0.1 electron volt, because each electron spectra consists of a number of vibration spectra. So the vibration spectra lies in the infrared region. And if you talk about rotational spectra, each vibrational energy level consists of a number of rotational energy level, and the the order of energy for rotational level is 10 to the minus 3, or rotational transition is 10 to the minus 3 electron volt, which lie in the lower energy, uh, with comparison to the visible and ultraviolet, that is far infrared and microwave region. So the correct option will be option A. I hope this is clear to everyone. Now we will move to question number 2. Question number 2 says Raman effect is the scattering of light with option A nucleus, option B molecules, option C protons, or option D electrons. So question says the Raman effect is the scattering of light with option A is nucleus, option B is molecules, option C is protons, or option D is electrons. So I'll give a few minutes to think about the correct answer, and then we will discuss. So, before discussing about the correct answer of this question, now let's discuss briefly about the experimental setup of Raman spectra. So, if you talk about the experimental setup, so it is suppose so there is a source, or the source of light which will be incident on the substance that will be which will absorb light, or uh, so we need a light source. So there is a light source initially. This is a light source. Then there will be a filter. This is a filter. This is a light source. Then there is a Raman tube. So there is a Raman tube. So there is a Raman tube, and the at the wall of the Raman tube, cold water, the running cold water is provided in order to provide the cooling of the tube, which will avoid the breaking of the tube due to the light. So light is, and in order to have the minimum loss, so there are reflective mirrors at the two sides of the tube, and that are coated with black body. So these are coated with black body. And also this is the glass tube. This is the glass tube, and the one part is open towards the spectrometer, which will collect the spectrum. So then there is a spectrometer is placed here. This is a spectrometer. So this is a slit and this is a lens. So the other part is also made a conical shape in order to minimize the reflections and maximizing the spectra. This is also covered, and the substance or the substance of which we want to study the Raman spectra is filled inside the tube. Basically, it is incident. It is filled in form of a gas or liquid. So when light is incident, so there is interaction of light with the molecule. So the correct option will be the molecules. So when the incident light is basically which is electromagnetic spectrum, that will be incident on the liquid or the sample, then the molecule present in that liquid or in that species, it will absorb light, or it will it will absorb the photon, or it will be scatter. So it will otherwise they will scatter the photon, and correspond to this phenomena we will be getting the spectra. That will be the components of Raman spectra, that is Rayleigh spectra, a Rayleigh line, Stokes line, and anti-Stokes line. So the correct option here will be molecules. So the Raman effect is the scattering of light with molecules. So the scattering of light with electron is called as Compton effect. So this is Compton effect. So I hope this is clear to everyone. Now we'll move to the third question. The question says, identify the wrong statement or statements where J is the rotational quantum number. Statement 1, it says delta J equals to plus minus 2 is the selection rule in Raman rotational spectra. Statement 2 says delta J equals to 0 is the selection rule for Rayleigh scattering. Statement 3 says Stokes lines are of shorter wavelength than that of the original line. So these are the three statements, and the options are option A, statement 1 and statement 2. So basically we need to find out or identify the wrong statement. So option A is statement 1 and statement 2. Option B is statement 2 and statement 3. Option C is statement. So I think this option should be statement 3 only. So it will not be 2. It will be statement 3 only, and option D is statement 2 only. So these are the four options, and we need to identify which of these options or option are each wrong. So we will discuss in a few minutes. So I would like you to think about this question, what will be the correct option, and then we will discuss it briefly. So if we discuss, so at the beginning of the today's session, we are discussing the concepts of the pure rotational spectra and the Raman rotational spectra and Raman vibrational spectra, and there we have discussed delta J equals to plus minus 2 is the selection rule for Raman rotational spectra, Raman rotational spectra. So option statement 1 is correct. Then if you come to statement 2, the statement 2 says delta J is equal to 0 is the selection rule for relay scattering, and we know what is relay scattering. When the relay scattering, when the frequency of incident light is equal to the frequency of scattered light, this is called as the relay scattering. So since the two frequencies are equal, the selection rule will be delta J is equals to 0. Delta J equal to 0 means there will be no change in energy, so the frequency will be remaining the same. So this is the selection rule for relay scattering, that is delta is equal to 0. So statement 2 is again true. Now if we talk about statement 3 says Stokes lines are of shorter wavelength than that of the original line. So if you remember the spectra of the if you remember the Raman spectra at the beginning of the session we are discussing. So at the central part, this is relay line. And this is Stokes line. This is anti-Stokes line. So the intensity of Stokes line is more than the intensity of anti-Stokes line. So now here, if you see, this is the frequency axis. So the frequency of Stokes line is less than that of the frequency of the actual line or the incident light. So since the frequency is less, so its wavelength will be longer. So the wavelength of Stokes line will be greater than the wavelength of incident line. The wavelength of incident light. So the statement 3 is not correct. So Stokes lines are of longer wavelength than that of the original line. So here the wrong statement will be statement 3 only. So the correct option is option C. So the correct option is option C. I hope this is clear to everyone. Now we'll move to the next question. Question number 4. Question number 4 says the gap between two consecutive Stokes or two consecutive anti-Stokes lines in rotational Raman spectra in terms of wave number. It is given that the rotational energy is given by HCB J into J plus 1, and the rotations have their usual meaning. That is, H is the Planck constant, C is the velocity of light in vacuum, J is the rotational quantum number, and B is the rotation constant. And the options are option A 4B unit, option B 3B unit, option C 2B unit, or option D B unit. So these are the four options, and we need to find out the correct answer. And the question says the gap between two consecutive Stokes or two consecutive anti-Stokes lines. So I'll give you a few minutes to discuss. I will give you a few minutes, and then we will discuss what will be the correct option. That is, what will be the gap between the two consecutive Stokes line or two consecutive anti-Stokes line in Raman spectra. So we had discussed about Raman rotational spectra and the rotational labels as the energy J into J plus 1 DHC. And if you talk about the selection rule, selection rule is delta J equals to plus minus 2, and we had obtained that from transition from J to J plus 2 prime equals to 4 J plus 3 by 2b, and when the transition occurs from J to J minus 2, it is minus 4 J minus 1 by 2 b. So this is anti-Stokes line, and this is Stokes line. So if we draw the spectrum of rotational spectra, so this is, suppose this is J equals to 0, this is J equals to 1, this is J equals to 2, J equals to 3, J equals to 4, and we know for Stokes line, the transition occurs from J minus 2 to J, or J plus 2 to J, sorry, and for anti-Stokes line, the transition occurs from J to J plus 2. So when the transition occurs from 0 to 2, 1 to 3, or 2 to 4, so this will be anti-Stokes line. And when the transition occurs from J plus 2 to J, that is, sorry, so this is J2 to J0, J3 to J1, or J4 to J2, then these are called as Stokes line. And if you talk about the value, so here you see, so when J is, so the transition occurs from J to J plus 2, so it will be J plus 3 by 2. So suppose this is 0, so suppose this is 0, so it will be 4 into 3 by 2b, so it will be 6b. So this will be, so that this will be occurring at 6b. So when J equals to 0, 4 into 3 by 2b, that is 6b. When J equals to 1, so here we are talking about anti-Stokes line. So 1 means 4, 1 plus 3 by 2b. So 4 into 5 by 2b will be 10b. Then for J equals to 2, it will be 4, 2 plus 3 by 2b, it will be 4 into 7 by 2b, it is 14b. So this will be, if you draw the lines, so this is the spectrum, so this is the central part, so it will be 6b, it will be 10b, it will be 14b. Similarly, if we talk about the anti-Stokes components or the Stokes components, for Stokes line, we know what is the expression. The expression is minus 4 j minus 1 by 2 into b, minus 4 j minus 1 by 2 into b. So when j equals to 0, that is when the transition occurs from, that is when the transition occurs from j2 to j0. So in that case, minus 4 0 minus half b, sorry, so here so if you remember, so when the transition was occurring from j into j minus 2, in that case it was the expression. So when the transition occurs from j2 to j0, so here j will be 2, not, so here j will be 2, it will be 2, so 2 minus 1 by 2 is 3 by 2, so minus 4b into 3 by 2, so it will be minus 6b. Then j3 b minus 4, 3 minus 1 by 2b, so minus 4b into 3 minus 1 by 2 is 5 by 2, will be minus 10b, j equals to 4 minus 4, 4 minus 1 by 2b, so minus 4b into 7 by 2 is minus 14b. So here this will be minus 6b minus 10b minus 14b. So if we go to the question, then what it says, the gap between two consecutive Stokes or two consecutive anti-Stokes line. So here the gap is 4b, 4b. Here also the gap is 4b. So between two consecutive Stokes or between two consecutive anti-Stokes line, the gap is 4b. So the correct option will be option A, that is 4b unit, where b is the rotational constant. So b is the rotational constant, that its unit is in centimeter inverse. I hope this is clear to everyone. So this was about the spectra of pure Raman rotational spectra. So now, if you go to the next question, the question says the excitation wavelength of laser in the Raman effect experiment is 546 nanometer. If the fast Stokes line is observed at 552 nanometer, then the wavelength of the fast anti-Stokes line is, options are option A 540 nanometer, option B 542 nanometer, option C 544 nanometer, or option D 450 nanometer. So I will give you a few minutes to think about this question, how we will get the correct answer, and then we will discuss. So if we discuss this question, it says the excitation wavelength of laser in Raman effect experiment is 546 nanometer. If the fast Stokes line is observed at 552 nanometer, then the wavelength of the fast anti-Stokes line will be what? So if you remember, the this was the spectra, this was relay line, this was anti-Stokes line, and this was Stokes line. So if you remember, suppose the shift is delta nu, suppose the shift is delta nu bar, then if suppose this delta nu, the nu 0 bar is the original line, wave number, then delta s bar will be Stokes line wave number, delta as bar will be anti-Stokes line wave number. And we know the position of both the lines are at equal distance from the central line. So for Raman effect, delta nu 0 minus delta s is equals to delta s minus nu 0. So if we, so all these are wave numbers, so delta as, sorry, nu as, it will be 2 nu 0 bar minus mu s bar. So we know it is 1 by wave number, so 1 by lambda as is equals to 2 by lambda 0 minus 1 by lambda s. Here, what is lambda 0? Lambda 0 is 546 nanometer. Lambda 0 is 546 nanometer. That is the incident wavelength. Incident light wavelength. And Stokes line is 552 nanometer. So lambda s is 552 nanometer. This is Stokes line wavelength. So what will be 1? So 1 by lambda s equals to lambda 0 lambda s 2 lambda s minus lambda 0. So lambda as will be lambda 0 lambda s divided by 2 lambda s minus lambda 0. So if you put the values, so lambda as will be 546 into 552 divided by 2 into 552 minus 540 nanometer. So if you calculate 5 4 Uh, 546 into 552, it is 301392 divided by 2 into 552, 2 into 552, 1104 minus 540, it is 301392 divided by 564. 564. 301392 divided by 564. Sorry, this is not. This was 546. Lambda 0 was 546. So this was 546. This is 546. 546 means it will be 558. 558. So 558. So it will be 540.12. 540.12 nanometer. So the answer will be 540 nanometer. So the correct option will be option A, 540 nanometer. So if the excitation wavelength of laser is Raman effect is 546 nanometer and the fast Stokes line is at 552 nanometer, then the fast anti-Stokes line will be at 540 nanometer. So as you can see, the Stokes line is at longer wavelength than that of the incident line, and the anti-Stokes line is at shorter wavelength than that of the incident line. So I hope this is clear to everyone. Now we will move to question number 6. Question number 6 says the difference between fast Stokes line and fast anti-Stokes line in rotational spectra is given. Rotational energy is given by HCB J into J plus 1 in terms of wave number, and the notations have their usual meaning. So the question number 4, in question number 4 we calculated the difference between two adjacent Stokes or anti-Stokes line, but here we need to find out what is the difference between fast Stokes line and fast anti-Stokes line. The options are option A 4B unit, option B 8B unit, option C 12B unit, or option D 6B unit. So since we have discussed in more details about the question number 4, so I don't think it will be taking much time. So we will discuss in a few minutes. So you please need to try to find out what is the correct answer. So if you remember the spectra that we draw, uh, so it was 6b, 10b, 14b, anti-Stokes line, minus 6b, minus 10b, minus 14b. Stokes line. So the difference is 4b, 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 4b. But if you talk about the difference between fast Stokes line and fast anti-Stokes line, one is at 6b, another is at minus 6b. So the difference will be 12b. So delta nu bar will be 6b minus of minus 6b, that is 12b. So the correct answer will be option C, 12b units. I hope this is clear to everyone since we have discussed in more details the question number 4. How the value 6b, 10b, 14b, minus 6b, minus 10b, minus 14b is coming. So now we'll move to the next question. Question number 7. Question number 7 says the gap between two consecutive Stokes line in rotational Raman spectra in a linear diatomic molecule is 4160 meter inverse. Find the moment of inertia of the molecule. Options are option A 1.29 in 10 to the minus 47 kg meter square. Option B 2.7 in 10 to the minus 47 kg meter square. Option C 4.9 in 10 to the minus 45 kg meter square. Option D 7.15 in 10 to the minus 46 kg meter square. So we need to find out the moment of inertia of that molecule, and it is given that between two consecutive Stokes lines the difference is 4160 meter inverse. So again, this question is pretty much similar to the previous one. In previous one, we need to find, in the previous question there was the we need to find out the difference between the two lines. But so since we know the difference between the two lines, and in B there is the expression, the expression the expression for B contains the moment of inertia, the expression for moment of inertia is included in B. So from that value we can calculate what will be the moment of inertia of the molecule. So I'll give you 2 minutes to try this question and then we will discuss. So we know the gap between two consecutive Stokes line in Raman spectra is two consecutive Stokes line is 4b. Then we know from question 4b is equal to 4160 meter inverse. That implies b is 4160 by 4 meter inverse, which is 4140 meter inverse. And we know b is the rotational constant, and the expression for b is h divided by 8 pi square I into c, where I is the moment of inertia. That implies I is h divided by 8 pi square b into c. So if you put the values, what is the value of h? Value of h is 6.626 into 10 to the minus 34, 6.626 into 10 to the power minus 34 divided by 8 into 3.142 square into 1040 into c, 3 into 10 to the power 8. So if we calculate, it will be 6.626 divided by 8 into 3.142 square into 1040 into 3 into 10 to the power minus 42 kg meter square. So if we calculate it, I will be 2.7 into 10 to the power minus 47 kg into meter square. So this will be the answer. And if you see the options, the correct option will be option B, 2.7 into 10 to the power minus 47 kg meter square. This is a pretty much simple question. You just need to find out the value of B, and since the expression for B contains I, and that I can be calculated if you know the value of B. So now we'll move to question number 8. Question number 8 says some vibrational Raman transitions are given as, where V is the vibrational quantum number, V1 to 2, V1 to 3, V2 to 3, and V3 to 4. Which of the following, which of the above is wrong? Options are option A, V1 to 2, option B, V1 to 3, option C, V2 to 3, or option D, V3 to 4. So which of the following options will be correct, where the transitions are given V1 to 2, V1 to 3, V2 to 3, or V3 to 4. These are the 4 options, and we will discuss in a few minutes what will be the correct options. Till then, you just think about the question and what will be the correct option according to you. So if we see the question, so B 1 to 2, 1 to 3, 2 to 3, 3 to 4. So if you think about the transition from 1 to 2, then here delta V is 1, here delta V is 2, here delta V is 1, and here delta V is again 1. So if you uh, remember the selection rules of vibrational Raman spectra, so for Raman vibrational spectra, delta V is 1. This is the selection rule. So the correct option will be, which is the question says which of the above is wrong. So this is not allowed, because for V1 to 3 the delta V is 2. So option B will be the correct option, and the transition from 1 to 3 is not allowed. I hope this is clear to everyone. Now we move to question number 9. Question number 9 says a Raman line of 2575 Armstrong is observed when the exciting line is of 2500 Armstrong. Calculate the Raman shift. Options are option A 1165 centimeter inverse, option B 1080 centimeter inverse, option C 1775 centimeter inverse, or option D 1253 centimeter inverse. So Raman line is 2575 Armstrong and the exciting line is 2500 Armstrong, and we need to find out the Raman shift. So I'll give you a few minutes to think about this question and calculate what will be the correct answer, and then we will discuss. So if we discuss the wavelength of Raman line, so Raman line wavelength is 2575 Armstrong. Exciting line wavelength is 2500 Armstrong. So now, if we talk about the wave number, because the shifts, the options are given in terms of wave number, so we need to find out the wave number of Raman line and the wave number of exciting line. Then the difference will be the Raman shift. So for wave number for exciting line, it is 1 by 2500 into 10 to the power 8 meter inverse. So 10 to the power 8 by 2500 meter inverse. For Raman line, it will be 10 to the power 8 by 2575 meter inverse. So what will be the shift? So this is E, this is R. So what will be the Raman shift? The Raman shift will be minus R. So if we calculate it, it will be 10 to the power 8 divided by 2500. So it will be centimeter inverse because 1 Armstrong is 10 to the 8 centimeter inverse. So it will be 400. So it is 40000 meter inverse. Now for new R, 10 to the power 8 divided by 2575 centimeter inverse. It is 38835 centimeter inverse. 38835 meter inverse. So delta nu bar, that is Raman shift, it will be 40000 minus 38835 meter inverse, which is 1165 centimeter inverse. So the correct answer is 1165 centimeter inverse. So the correct option will be option A. So the wavelength of Raman line and the wavelength of exciting line was given to us. So in order to find the Raman shift in terms of wave number, we need to find out the wave number of exciting line and wave number of Raman line. So the correct answer will be option A, that is 1165 centimeter inverse. So I hope this is clear to everyone. Now we'll move to the question number 10. Question number 10 says, when an exciting line of 4900 Armstrong is used on a material, a Raman line of 5000 Armstrong is produced. Find the position of Stokes and anti-Stokes lines in Armstrong unit for the same material when the exciting line is of 4000 Armstrong. Note that the Raman shift is the characteristic of a material irrespective of the wavelength of the exciting line. Here the options are: option A, Stokes 4950 Armstrong, anti-Stokes 5050 Armstrong. Option B, 4300.4 Armstrong, anti-Stokes 3799.6 Armstrong. Option C, Stokes 4066.3 Armstrong, anti-Stokes 3935.7 Armstrong. Option D, Stokes 4245.7 Armstrong, anti-Stokes 3754.3 Armstrong. So the question was exciting line of wavelength 4900 Armstrong. The Raman line is of wavelength 5000 Armstrong, and we need to find out the position of Stokes and anti-Stokes line. If the same material, when the exciting line is of, so these are the, so this is the first case. So in case 1, exciting line is 4900 Armstrong, Raman line is 5000 Armstrong. So here we need to find out the Raman shift, and for case 2 it says the exciting line is 4000 Armstrong. Then what will be the position of Stokes and anti-Stokes line? So I hope the question is clear to you. Now we will I'll give you a few minutes and then we will discuss what will be the correct answer. So if we discuss, so the case one exciting line is exciting line wavelength 4900 Armstrong. So wave number is 10 to the power 8 divided by 4900 centimeter inverse, that is 20408 centimeter inverse. Now the Raman line wavelength is 5000 centimeter, sorry, 5000 Armstrong. So wave number will be 10 to the power 8 divided by 5000, that is 20000 centimeter inverse. So Raman shift, it will be the Raman shift, it will be 20408 minus 20000 centimeter inverse, which is 408 centimeter inverse. Now you see, it says, note that the Raman shift is the characteristics of the material irrespective of the wavelength of the exciting light. So whatever be the wavelength of the exciting light, the Raman shift will remain the same since the material is the same. So in case 2, so this is the Raman shift and it will be the same for a given material. Now if we talk about the second case, the exciting, what was the frequency of what was the wavelength of exciting line? It was 4000 Armstrong. So exciting line wavelength is 4000 Armstrong. So What will be the web number? It will be 10 to the power 8 divided by 4000 centimeter inverse. That will be 25000 centimeter inverse. 25000 centimeter inverse. So Stokes line, it will be at shorter wavelength. That is, Stokes line will be at shorter wavelength, and anti-Stokes line will be at Stokes line will be at longer wavelength, and anti-Stokes line will be at shorter wavelength. So we can say Stokes line will be at longer shorter wave number, and anti-Stokes line will be at longer wave number. So what will be the wave number for Stokes line? It will be 25000 minus the Raman shift, that is 25000 minus 408 centimeter inverse. And for anti-Stokes line, it will be 25000 minus, sorry, plus delta nu prime 25000 plus 408 centimeter inverse. So if you convert it to wavelength, then for Stokes it will be 1 by 25 408, means it will be 25 minus 408 is 24592 centimeter inverse. 24592, 1 by 24592 centimeter, and anti-Stokes will be 1 by 25408 centimeters. So it will come out to be 4066.3 Armstrong, and it will anti-Stokes will be 3935.7 Armstrong. So the correct option will be option, so it is 4066.3. So the correct option will be option C. I hope this is clear to everyone. Now we will move. So since we have time, we will solve another more question. So all these questions we solved today was based on the rotation Raman spectra. Now let's solve another question related to vibration Raman spectra. The question says, in a vibration Raman spectra of HF molecule, the Raman lines are observed at wavelengths of 2670 Armstrong and 3430 Armstrong. So Raman lines were observed at 2670 Armstrong and 3430 Armstrong. Find the fundamental vibrational frequency of the molecule. Find the fundamental vibrational frequency of the molecule. So let's so since the wavelength is given, let's find the wave numbers. So the wave numbers of Raman line Raman lines will be 1 by 2670 into 10 to the power minus 8 centimeter inverse, and 1 by 3430 into 10 to the power 8 centimeter inverse. So it will be 37453 centimeter inverse and 29154 centimeter inverse. And here we need to find out the fundamental frequency of vibration. So if nu be the wave number of the if nu bar be the wave number of exciting line and the Raman spectra will be delta nu, then what will be the shift? So the Raman shift, we know the Raman shift is nu plus delta nu minus delta nu by 2. That is there will be shifting in both sides. One is nu plus delta nu, another is nu minus delta nu. So nu plus delta nu is 39154 minus 37453 divided by 2. Sorry, let me add another slide. So the Raman shift delta nu will be 4149.5 centimeter inverse. This is the value of Raman shift. Then this is the same as the vibrational constant omega. So the Raman shift is equal to the vibrational constant, because we at the beginning of the session we had discussed the selection rule is delta V is plus minus 1. So the shift will be equals to plus minus omega or omega E. So this omega will be 41. So omega will be 4149.5 centimeter inverse. So vibrational constant omega will be again this much. So, and we know what is the relationship between the frequency of oscillation and vibrational frequency. So the oscillation frequency and vibration frequency, it is omega into C. So omega is 4149.5 into C is 3 into 10 to the power. Since this is centimeter inverse, so C should be in centimeter inverse. So it is 3 into 10 to the power 10 centimeter per second. So if you calculate it, it will give you 1.24 into 10 to the power 14 hertz. So what is the answer? The oscillating frequency, the frequency of oscillation is 1.24 into 10 to the power 14 hertz. I hope this is clear to everyone. So this will be the this type of problems that are based on. So these are, and this is an example of a problem that is based on the concept of Raman vibrational spectra. So with this we come to the end of today's interaction session. I hope this will be quite useful for solving your assignment problem as well as the problems that will be appearing that will be you will be facing if you are appearing for the exam. So also there will be another extra interaction session that I will take tomorrow at 7:30 to 8:30 p.m. And in that interaction session, I will give a brief overview of the whole course content that you have been taught across these 12 weeks. So till then, that's it from my side.